All right, let's take a look at cracking LFSR stream ciphers. And in particular, we're going to be using a known plaintext attack. And as a reminder, a known plaintext attack is a method that can be used where you guess a piece of the plaintext. You don't need to know the whole thing, but just a little piece. And then from that piece of the plaintext, we're going to generate what we think to be the key stream that was used to create the message. And we'll do that by using the XOR operation with the ciphertext and our guessed plaintext. Once we have that bit of the key stream, we'll work that backwards to determine the initial seed value of our LFSR system. And once we've got that, we can generate as much of the key stream as we need to decipher the entire message. So let's suppose we intercepted the following message. We got 48 U, W, M, E, V, I, so on. Looks like base 64 characters. And we'll assume that we know a little bit about the system. We'll know that it's a 7-bit LFSR, and the rule is such that the previous states of bits 2 and 5 XORed together will give us this current state of bit 7. And that might seem like a lot that we're assuming that we know about, but the thing about an LFSR cipher is that these are often implemented in hardware, meaning that it's hardwired into some sort of device in order to do the encryption, which means that if you can recover just one of these devices, this is pretty easily discernible by looking at the circuitry of that device. So oftentimes it's a safe assumption to make that you know a little bit about the system and how it works. What we don't know is the initial seed value. So in this case, that is going to be what we consider to be the key of the system. Once we've got that seed value, we can do whatever we want. We can decipher the entire message. We can encipher our own messages using the exact same setup. So that's really what we're going for. Now, typically with a known plaintext attack, you need to know a little bit about what you think the message is regarding. So in this case, we'll think that it's about some sort of programming language. And that might help us make an educated guess about the known plaintext. So let's suppose that we think that the programming language they're talking about is the programming language Ruby. So maybe we think that the word Ruby lines up with the first 4 characters of our ciphertext. And what we'll do to kind of make things a little bit easy is we won't convert all of these things into binary, which is the way the LFSR system works. We'll just take the first 2 characters of each, and we'll see that that's actually going to be enough. If we can guess the first 2 characters, that's all we need. So we'll convert both of these, both the first 2 characters of the ciphertext and the first 2 characters of our guessed plaintext into binary. We're going to do that using our base 64 conversion. So each of these characters is represented by 6 bits. And we've got now our binary ciphertext and our binary guessed plaintext. And if we XOR those 2 things together, we're going to be able to generate the key stream. Remember, with the way that this type of cipher works is that if you've got your plaintext, your ciphertext, and your key stream, you can pick any 2 of them together and XOR them to get the third one. So in this case, we have the ciphertext and what we think is the plaintext. So if we XOR those together, we'll get what we think to be the key stream. Just like how if you're making a message, you would take your plaintext and XOR that with the key stream in order to get the ciphertext. And when you're decoding the message, you would take your ciphertext and XOR that together with the key stream to get the plaintext. So now that we think we know what the key stream is, we can try and reverse that back to get our initial seed value. So we'll kind of set up a table here, just like we do when we generate a linear feedback shift register system. Only the information we got goes down the first column. Those are our bit 1 information. Using our transition rules, we know that the information in column 1 was generated along the diagonals, starting on the top row all the way down, moving down and to the right. So if we kind of work those things back up and to the left, we can see that we can already work our way back up to the seed value. We only needed 7 bits of the key stream because they were in the first position of our ciphertext. We're able to work all those back up to the seed value. And we actually have a little bit more information because we guessed 12 bits of information. We can work those up as well. And what that allows us to do is do a quick check. If we actually guess those 12 bits right, all of the entries that are currently in the table should be valid to the definition of the system that we know to be true. So if we were to look at bits 2 and 5 and see if they can predict the next bit 7, the very first pairing we see is actually incorrect. Bit 2 and 5 are 0. The XOR of a 0 and a 0 is a 0, but there's a 1 there. Now you'll see that some of these are correct. There's a 1, 1, which is a 0. Oh, a 0, 0, which is a 0, a 0, 1, which is a 1. There's another error message. And what we see is that the fact that we have information now in the table that's inconsistent with the definition based off of the key stream that we guessed means that we made an incorrect guess on our plain text. So you're definitely going to see that happen when you make an incorrect guess about your plain text. So we got to go back to the drawing board here. So maybe we guessed Ruby wrong. It's not about Ruby. We might have also just guessed that Ruby was in the wrong spot. Maybe we could have slid it over a position and it would have worked fine. But in this case, let's just try a different plain text word. Instead, we'll try Python. And we'll go through the same exact process. We'll take the first two characters, we'll convert them to binary, we'll XOR those binary streams together to get our supposed key stream. Notice it looks a little bit different. And then we'll put that down the first column of our LFSR table. In the same way, we'll use those transition rules to move those bits up and to the left along the table, because we know that's how they get moved around in the table from iteration to iteration. So we've moved those up and to the left, and we'll move up the additional information to help us check to see if our guesses were right. Starting at the top, bits 2 and 5 XOR correctly in the first iteration, second iteration, third, fourth, and fifth. No evidence of an incorrect guess so far. And what we can continue to do now that we think we're on the right track is generate more bits in the table. So we'll take bits 2 and 5, and then we'll XOR them together to fill in the next one, and then we'll transition that new character 1 down and to the right. We'll XOR the 1 in the 0 to get our new bit down here, which would be a 1. And we can continue doing that, filling up the entire table, and then filling it up even further to keep generating future values of the key stream. If we were to convert the entire ciphertext message into binary, we'd see that written here. And if we were to use that seed value we determined, which was 0, 1, 1, 1, 0, 1, 1, those were the values across the top row on our LFSR table, and we kept generating future values of the key stream until we had equal number of bits as our message, we can now XOR those together. We won't show the whole message here, but we'll see the first about 18 bits or so. If we were to XOR the ciphertext in the key stream, that should give us the plain text. And if we take that plain text and convert each 6-bit binary chunk into its corresponding base 64 character, we'll see that we get the following message: Python is the best, which is actually an English phrase, so it seems to suggest that our guessed plaintext was correct. It generated the rest of the word Python for us and then kept on going to generate the rest of the plaintext message. And that's how a known plaintext attack works. You guess the plaintext, you convert the ciphertext and your guessed plaintext to binary, XOR them together, use that key stream to kind of work your way back up to get to the seed value, make sure that everything works out correctly in your table, there's no contradictions to the definition, and then use that seed value and definition to generate as much of the key stream as you need to XOR with the full ciphertext to get you your plaintext.